We looked at Lewis structures as a way to distribute electrons in a molecule, but Lewis structures don't really give us a good idea of three-dimensional shape. In order to get three-dimensional shape, we need to use something called valence shell electron pair repulsion theory. So the whole point of valence shell electron pair repulsion theory is electrons repel each other. Makes sense, right? Electrons are negative. Negative-like charges repel, so negative repel negative. And in three-dimensional space, those negative charges are going to repel each other in a way that gets them as far apart as possible while still bonded to the central atom in the structure. So to draw a good Lewis structure, or a good VSEPR structure, the first thing we have to do is start by drawing a good Lewis structure. Because Lewis structures tell us how the electrons are distributed between the atoms. We then use that to see how those electron pairs repel each other. So after drawing a good Lewis structure, we're going to count the regions of electron density around the central atom. A region of electron density is any bond, doesn't matter if it's a single, double, or triple, or any lone pair. Once we count the number of regions of electron density, we're almost there. The electron geometry is defined by the number of regions of electron density. And for our purposes in this class, we're only going to work with 3 electronic geometries. If we have 2 regions of electron density, it's a linear electronic geometry. If we have 3 regions of electron density, it's trigonal planar. If we have 4 regions of electron density, it's tetrahedral. Now, I've been very careful to always talk about electronic geometry, because the electronic geometry is something that's defined by those valence shell electron pair repulsion interactions. Once we know the electron geometry, we know the ideal angles in the shape that we're dealing with. But what we really want to know is molecular geometry. And molecular geometry is defined only by the bonds that make up the molecule, or if you want to think about it, only by the atoms that exist. So lone pairs don't define molecular geometry exactly. Lone pairs are used in defining an electronic geometry. So after you have your good Lewis structure, when you've counted your regions of electron density, take note of the number of lone pairs, and then we've got a handy little chart to look at. But before that, just a note here. If you have no lone pairs on the central atom, that's the easy case, because then the electronic geometry and the molecular geometry are exactly the same. The only time the molecular and electronic geometries are different is when we've got lone pairs to work with. So here's a handy little chart. This is in your textbook. So this is regions of electron density. So number of bonds and lone pairs is what I've been calling regions of electron density. We're either going to deal with 2, 3, or 4. Those are our only options. Number of lone pairs. Here we go. Not sure. That's goofy header in the table in your book. But if we've got 0 lone pairs, then that's what I just described. 0 lone pairs means it's all bond, which means the electronic geometry for 2 regions of electron density is linear. With no lone pairs, the molecular geometry is linear. 3 and 3, trigonal planar, tetrahedral. If I've got 1 lone pair, then I've only got 2 atoms left for linear, so that's linear as well. For my trigonal planar, I now have a lone pair that doesn't count in the molecular geometry, so we would call this molecular geometry bent or angular. Similarly with tetrahedral, if we change one of those to a lone pair, this is now a trigonal pyramid. 2 lone pairs will give us a bent or angular based on tetrahedral electronic geometry. Now, a couple of quick things to point out here. This table talks about, or this table includes information about bond angles. And you see that the bond angles change when we go to a lone pair. In valence shell electron pair repulsion theory, a lone pair takes up more space than a bonding pair. So this pair of electrons is closer to the central atom, which pushes these two away from each other, away from that lone pair. So it squeezes this angle down. You can see that in this case. You can see it here. This ideal angle is 109 degrees. In a trigonal pyramid, it's a little bit less than 109. In a bent or angular, it's even less than it was in the trigonal pyramid. The other thing you see here is you start to see some conventions in how chemists draw molecules and imply direction. So when I've got something that's just a stick, just a straight line, that implies that it's in the plane of the page I'm working with. If I've got something that's a solid wedge like this, that is sort of meant to imply some perspective, and it's coming out of the page at you. The dashed wedge implies that it's going into the page away from you. So we're going to be seeing these types of pictures a lot, so they're going to start to make more sense and feel more natural to you as we move along. So if we look at a couple of examples, I just pulled these off of our Lewis structure example because that's the first step, right? So methane, what do we have? We've got 1, 2, 3, 4 regions of electron density. 4 regions of electron density means my molecular or my electronic geometry is tetrahedral, and no lone pairs means that my electronic geometry is likewise tetrahedral. So that's what this looks like in 3 dimensions, 109-degree angles between each of these hydrogens. If we get on to carbon dioxide, right? Carbon dioxide now has, 1, 2 regions of electron density. They're double bonds, but each double bond still only counts as 1 region of electron density. 2 regions of electron density, no lone pairs again. So we've got a linear molecule. You would expect a 180-degree bond angle there. What about ammonia? Ammonia has 3 bonding pairs and 1 lone pair. So 4 regions of electron density means we've got a tetrahedral electronic geometry, but with 1 lone pair, the molecular geometry here is trigonal pyramidal. So these angles should each be a little bit less than 109 degrees. As I said, we're going to be looking at a lot of structures. We're going to be looking at a lot of these on paper and building a lot of these. So they'll start to make a little bit more sense. You'll start to get used to them. And as always, practice always helps. So good luck on that, and I will see you in the next video.